Okay, calculate support reactions. Let me move this up a little bit so you can see this. Okay, calculate the support reactions of this. Okay, so it looks like I've got a gable roof here. A gable roof just means two sloping sides. This would be more of a salt box style. A salt box, one side is steeper than the other side. So I have this frame, the two sides of the frame, A, B, D, E, those are the two sides. BC is a sloping part of the roof. CD is a sloping part of the roof. Here's a hinge at the ridge line. I've got wind coming in from the left, a windward side, a leeward side. And this building is on somewhat of a hill here. At point A there's a pin. At point E there's a pin, and there's a little hill going up here. So side DE is not as long as side AB. And please take note of all the dimensions here. For these triangles that make up what looks like the roof, we call these primitive Pythagorean triangles. Take a look at this triangle here. I've got one leg that's 35, one leg that's 12. The hypotenuse is 37. So that forms a Pythagorean triangle, a primitive Pythagorean triangle. And then I've got another Pythagorean triangle here, 5 feet, 12 feet, 13 feet. So two primitive Pythagorean triangles that make up the roof. Now I call them primitive Pythagorean triangles because if you double these lengths you also get a Pythagorean triple. But it's not a primitive Pythagorean triple. To be a primitive Pythagorean triple, the three sides have to have a greatest common factor of 1. Okay, so one Pythagorean triple, 35, 12, 37. And then the second one, 5, 12, 13. And notice the forces on here. I've got a distributed wind force. I'll call that 20 pounds per foot. It usually gets stronger towards the top, but just for simplicity I make this a uniformly distributed load. Normally there's suction on the windward slope of the roof, but it looks as though that windward side is so steep that I wouldn't anticipate there would be any suction, so I'll just model this as almost a vertical wall, that really steep portion of the roof. I do have suction on this side though. And I've got suction on the leeward side. So I want to find all the support reactions. I've got 2 reactions at A and 2 at E. And I'm going to redraw all this. I want to resolve the distributed load along DE into its resultant force, which will go through the midpoint of this wall. And then I want to resolve this suction force into its resultant, which will act in the middle here. Exactly between C and D, and then I'll break this distributed load, the portion here. I'll break that up into its resultant force. So I should say I'll resolve that into its resultant force, and then between A and B I'll resolve that into its resultant force. So all of these distributed loads, I'm going to turn them into their resultant forces. Okay, breaking these into their resultant forces, I get this figure right here. Okay, now where did these come from? I'm going to move this down a little bit. Okay, so the 600, where did I get that? 20 pounds per foot times 30 feet. The 240, that's 12 feet times 20 pounds per foot. The 185 acting normal to the slope, that's 5 pounds per foot times 37 feet. The 250 pounds on wall DE, side DE, that is 10 pounds per foot times 25. Okay, so I took these distributed loads and I turned them into their resultant forces. Now these distributed loads that I'm showing here, these are just numbers that I came up with for this simple example. They may or may not be realistic. If you're really doing a wind design, you should consult with your local building code or do some kind of wind tunnel test. But just using these numbers that I made up for example, I get these resultant forces right here acting at the locations you see them acting at. One more thing I want to mention with regards to those distributed loads. So let me bring back the previous slide. For the steep portion of the roof right here, I'm using what's often called the projected area method. The projected area method meaning that I am modeling the wind load on this slope as a purely horizontal load. Notice that I'm not showing the distributed load normal to the sloped portion of the roof. I'm showing a purely horizontal. That's sometimes called the projected area method, which would probably be reasonable in this case because this is very steep anyway. But for the other wall, the other slope on the roof, that's not as steep. So I'm using what's called the normal force method. The normal force method is where I show the distributed load acting perpendicular to the slope. So on the left, the windward side of the frame, I'm using the projected area method. On the right side of the frame, or the right side of the slope of the roof, I'm using the normal force method. So you would consult your building code for advice on which method would be better. Also, there's usually suction on both slopes, but this would be a bit of an unusual case. There might be a little bit of suction on this portion of the roof, but it's so steep that I'm just I'm almost considering it vertical because it's so steep. So normally there'd be suction on both slopes. In this case, I'm just considering the suction on the longer slope. So my point is that if you're doing a wind design, you should probably at least consult your local building code or whatever code you're adhering to, or maybe even do a wind tunnel test, consult an aerodynamicist with regards to that. So anyway, I turn all these into their resultant forces and I get this. Okay, so copy this down. Okay, one more thing I want to do. I want to take the 185 that's normal to CD, and I want to break that up into a horizontal and vertical force. Okay, and like magic it gets done. So the 185, I cross it off here because I'm replacing this vector with a vertical. See that 185 cosine gamma? And this is 185 sine gamma. What is gamma? That would be this angle right here, gamma. See it there? Meaning that this would also be gamma right here. Meaning that this would be gamma right here. So make sure you understand the geometry here. Also notice off to the side here, since I've got a Pythagorean triple here, this is a Pythagorean triangle. Because I've got a Pythagorean triple in the numbers 35, 12, and 37, they form a Pythagorean triple. So I'm able to find the sine and cosine of angle gamma exactly, 12/37 and 35/37. So I might need this information in a few moments. So now I've got the 185 cosine gamma vertical, 185 sine gamma horizontal. So now I'll take the sum of the moments about point A, and I've got an A sub y down there. I think that was cut off. Okay, so take the sum of the moments about point A. Okay, now take a good look at what the moment arms are here, because I'm going to throw that calculation out of the next slide. The sum of the moments about point A, I'm going to say that counterclockwise is positive. Okay, ready for this? Okay, the sum of the moments about point A is 0. Do you know where I'm getting these? E sub y times 40. Okay, remember it's the moments about A. So E sub y is right here. 40, where am I getting that 40? The moment arm, the distance between my finger and the pencil, that's 40. 17.5, 17.5 plus 5. Plus E sub x times 5. Okay, here's E sub x. Tends to want to rotate, what is that, counterclockwise? Moment arm 5. Minus 250 times 17.5. What am I talking about? That would be this 250 right here. Okay, and it rotates it in the clockwise direction. Moment arm 17.5. 12.5 plus 5 is 17.5. Plus 185 cosine gamma. Okay, so I'm right here. I'm talking about this vertical force here. Okay, what is the distance between that and A? Here, I'll use 2 pencils. Okay, how does this look? The moment arm, I'll get it right eventually. 5 plus 17.5, what is that, 22.5? Okay, so there's the 22.5. Minus 185 sine gamma 36. What's that? 185 sine gamma. Be careful, I'm showing it here, but it's actually acting down here. They're acting at this point. Both these vectors are acting at this point. So the moment arm on that, 36. Where am I getting that 36? 12.5 plus 12.5. What is that, 25? Plus 5 is 30, plus 6 is 36. Is that what I said? 36. Minus 240 times 36. That would be this 240. 36. 15 plus 15 plus 6. Okay, where am I? Minus 600 times 15. That's referring to this 600 here. Moment arm 15. So I think that's everything. So I took all my forces starting at E, going around the silhouette of the frame. Okay, so I'm going to clean this up. I've got 2 unknowns here, E sub x and E sub y. I'm going to clean all this up, and remember that I know the exact values for cosine of gamma and sine of gamma. Remember those? They're right here. Okay, so clean all this up. Okay, so I do the arithmetic. I wind up with this equation here. I'll pause the video and double check if you want. Clean it up a little bit further and I get this, which is a standard form for a linear equation. 5e sub x plus 40e sub y is 20,237.5. I'll call that equation 1. Okay, well, 1 equation and 2 unknowns. I cannot solve that. So let me go back to my original drawing. See, there's a hinge here. So that hinge, I'm going to unbolt this frame at the hinge, and I'm going to consider this as 2 separate entities. I'm going to consider the left portion, and I'm going to consider the right portion. Okay, remember my second slide? Maybe this is a better picture to look at. Okay, so my next slide, I'm just going to analyze the left side of this. A blank sheet of paper here. Okay, so cover this up. My next slide, I'm just going to analyze this part. Now, when I unbolt it at C, I remember there'll be 2 reactions at C. Where you've got a hinge, you've got 2 reactions, a horizontal and vertical. So I'm going to unbolt this thing at C and analyze the left portion. Okay, and there it is, the left portion of the frame. See this? So I'm analyzing only the left portion. So remember this? Okay, I see the 600, I see the 240, I unbolted it at C, 2 reactions at A. That's what you see here. So up at the top left part, and I have a surprise for you. I also did the right part. So this is the right portion of the frame. Okay, go back to one of the previous drawings here. Remember this drawing? Okay, let me cover this up with my wonderful calculator. Okay, so now you can only see the right part of it, can't you? Okay, be careful. I mentioned this a moment ago, but you see the 185 sine gamma? I probably should have drawn that down here. This might be a bit misleading, but that horizontal is actually acting down here at the point of contact with the slope of the roof. So just be careful with that. Okay, so I redraw this portion of the frame, and that's what you see right here. Oh, and I fixed that issue with a 185 sine gamma. In the previous drawing, I had it up here, but it's actually down here, so this is maybe not as misleading. And I threw the dimensions on there for you, so make sure you understand these dimensions. Be careful, I kind of ran out of space over here, so I put the 12.5 and 12.5 on this side. So my draftsman's work isn't too good, but I hope you get the idea here. Alright, so now let's look at the whole thing, or I should say both parts. Maybe I can't fit that in one screen. Okay, so I've got the left half and I've got the right half. So I'm going to analyze these 2 independently. So first I'm going to analyze the left half, which is this portion here. Let me cover this up with my wonderful graphing calculator. So if I analyze this portion, I'm going to take the sum of the moments about point A. Okay, so that'll be the next calculation. You see, the sum of the moments about point A. And that's what I'm talking about. So analyzing the left, the sum of the moments about point A. Okay, just look at this portion. Sum of the moments about point A. Okay, pause the video and get a good look at this if you need to. When I take the sum of the moments about point A, I get this equation right here. Clean it up and you get what I call equation 2. Okay, well, one equation and two unknowns, so what good is it? Well, it might be good in a few moments here. Okay, go back to this picture. Okay, now I've analyzed the left, so now I'm going to analyze the right portion. So it's right here. Okay, what can I do here? I propose taking the moments about point E. Here's point E. Take the moments about point E. Okay, so get a good look at this picture, because now I'm going to analyze the right portion of the frame and take the sum of the moments about point E. Okay, so here was my calculation analyzing the left, so now I'm going to say analyze the right by taking the sum of the moments about point E. And so I get this, analyzing the right, sum of the moments about point E is 0. Okay, you know where I'm getting all these figures from? I sure hope so. C sub x times 37. C sub x, where's the 37 coming from? Okay, that's the moment arm. 12.5 plus 12.5 is 25. Plus 6 plus 6, that's the 37 part. C sub y times 35. C sub y wants to rotate this thing counterclockwise about point E. 17.5 plus 17.5, 35. 185 cosine gamma, that's this one. Moment arm 17.5. Remember, it's the moments about point E that we're talking about here. Okay, and then what about 185 sine gamma times 31? 185 sine gamma, what's the 31? 12.5, 12.5, that's 25 plus 6, that's 31. Where am I? Minus 250 times 12.5. So that must be this one. 250, 12.5 foot moment arm. Okay, and remember, I know the exact values for sine gamma and cosine gamma. So now I'm going to clean all this up. And like magic, it appears. Okay, so cleaning up the equation. Negative 37 c sub x plus 35 c sub y minus 3062.5 minus 1860 minus 3125. Clean it up and you get what I call equation 3. So really what I have here are two equations and two unknowns. Equation 2, equation 3, with the same pair of unknowns, that is c sub x and c sub y. So I'm going to solve this system of two equations and two unknowns, probably using a matrix. Although only two equations and two unknowns, I don't really need a matrix, but I'll use a matrix anyway. Okay, remember how to do this from linear algebra? Okay, so I set up some matrices here, the coefficients, the variables, and the constant terms. So here's a famous matrix equation. If A times C is B, then C would be A inverse times B. So you can do this in a graphing calculator. So solving for the C sub x and C sub y, I get, these are actually approximations. I don't know how many more digits that decimal would have. A more exact answer would be over here. So C sub x, 230,865 divided by 662. C sub y, 198,135 divided by 331. Okay. Or I could say C sub x is approximately 349 pounds. C sub y about 600 pounds. Okay, I want to stick with the exact answers, which are these weird-looking fractions. So let me go back to a previous drawing. Remember this? Okay, so let me write these on the drawing. So C sub x, what is that? 230,865 over 662. Okay, I'm getting a little carried away here in terms of exact figures. Okay, and then the C sub x, okay, now that's also true over here. Okay, remember Newton's third law? Remember Newton's third law? For every action, there's an equal and opposite reaction. So notice that if I analyze the left, I've got C sub x pointing to the left. If I'm analyzing the right portion, I've got it pointing in the opposite direction. So notice that the C sub x's are opposite of each other. Same thing with the c sub y. So c sub y, what is that? 198,135 divided by 331. Same thing over here. Okay, equal and opposite. For the left, I've got c sub y going up. For the right, I've got it going down. So be careful when you cut a structure at a hinge like that, you're going to have the equal but opposite reactions like you see there. Okay, what good does this do me? Okay, let me go back to the left portion. Do I have enough information to find a sub x and a sub y? I sure do, so that's what I'm going to do, find a sub x and a sub y. Okay, here's the left portion of the frame. Analyze it. Sum of the forces in the x direction is 0. Negative a sub x plus 600 plus 240 minus c sub x, which is this, is equal to 0. Okay, so that's what I did here. So from the left portion, okay, this is what I just read to you. Okay, so pause the video if you have to. I wind up with a sub x is this exact value here. This is an approximation. Why don't I do the same thing in the y direction? So sum of the forces in the y direction, we're just looking at the left portion here. Sum of the forces in the y direction, a sub y plus c sub y is 0. C sub y is this weird looking fraction. Okay, that's what I'm doing here. A sub y plus c sub y is 0. Stick in that weird looking fraction. A sub y is negative 198,135 divided by 331. A negative meaning I assumed the wrong direction. So here's my a sub x. I'll use the exact value. Here's my a sub y. Write those on the figure. Okay, so write those on the figure. A sub y, I'll use the exact value. So this is negative, where am I? 198,135 divided by 331. Forgivable if you use a decimal approximation. Okay, and then the a sub y part. A sub y part, that's what I just did, the a sub y, the a sub x, I mean. $325,215 over 662. Okay, that's the a sub x. So a sub y is actually going down. Does that make sense logically? That I've got a sub y going down? Yeah, probably. Take a look at this figure. It seems as though this thing is going to want to pivot about point E, so there would be a reaction that would tend to go down there. Okay, what have I got here? So it looks as though I've got everything for the left portion. For the right portion, what do you suggest I do for the right portion? Well, why don't I do an analysis for the right portion? Take the sum of the forces in the x direction, sum of the forces in the y direction. Remember that I know cosine gamma and sine gamma, so I'm going to find e sub x and e sub y. So I'll analyze the right portion of this frame, take the sum of the forces in the x direction, the sum of the forces in the y direction, set it equal to 0. So that's what I'm doing here. So the sum of the forces in the x direction is 0. Okay, take a good look at it. Pause the video if you have to. E sub x is this value, exact value. This is the approximation. E sub y, I'm taking the sum of the forces in the y direction. Sum of the forces in the y direction is 0. I get e sub y is this exact value. Okay, pause the video if you have to. I'm going to write these on the illustration. Okay, so get those values. Go back to this illustration. So, e sub x, I'm going to use the exact value. $436,085 over 662. Very forgivable if you just use the decimal approximation. And then the e sub y part. 140,210 divided by 331. Okay. So now I have all four reactions, don't I? See that? Where's my original drawing? Okay, found it. Okay, here's my original drawing. So now I know all four reactions, the two reactions at A, the two reactions at E. Okay, so now I'm going to redraw the whole thing, but for my final drawing, I'm just going to show the external reactions. I'm not going to redraw all these distributed loads. So I have here the frame with all the reactions at A and E. Notice that? And I put those yellow circles around them, those yellow rectangular shapes around my reactions. Okay, now one thing I didn't mention, remember this slide? Remember equation 1? Did I ever use that? I don't think I ever used equation 1, did I? What's E sub x and E sub y? Do I know those now? I challenge you to put this number and this number, E sub x and E sub y, in equation 1 to verify that equation 1 is in fact satisfied. And one more thing I should probably do is draw all the original loads on this so that we can see the final drawing in all of its completeness. So I stick E sub x and E sub y into equation 1. So I say it has been found that E sub x is this fraction, E sub y is this fraction. This was equation 1. Replace E sub x with its value. Replace E sub y with its value. It does work, so I say aha. So equation 1 is satisfied. Remember that that was based upon the moments about point A for the entire frame. Okay, so here's my final drawing with all the initial loads and all the final reactions. One more thing I can do to check this. Remember that equation 1 was based upon the moments about point A. Why don't I check the moments about point E and make sure that it is in static equilibrium? So for this final picture, I guess I need to resolve these distributed loads into their resultants. So once I do that, I'm going to check the three equations of equilibrium. Sum of the forces in the x direction is 0. Sum of the forces in the y direction is 0. The sum of the moments about point E is 0. I already checked A. I have equation 1 for A, so I'm going to do the moments about E. Okay, look what I did here. I resolved the distributed loads into their components. 840. Okay, I've got 20 pounds per foot times 42 feet. That's to 840, you see, acting on the left side. The distributed load on the sloped portion of the roof. 185. What is that? 5 pounds per foot times that length. I believe that was 37. Okay, so I get the 185, and then I broke that up into horizontal and vertical components. So there's 185. Now that you see it, I'm going to lightly cross it off because that gets replaced with 175 vertical right here and a 60 horizontal based on angle gamma. And then on the leeward wall, where I've got suction, 10 pounds per foot times 25 feet, that's 250 pounds. Okay, so I'm going to consider the equilibrium of the entire frame. The sum of the forces in the x direction is 0. What's in the x direction? A sub x, A sub x to the left, 840 to the right. Okay, here I've got it. 840 to the right, so it's positive. This right here is A sub x. The 60 and the 250, what are those? The 60 is this right here, 60. That is the horizontal component of the resultant acting on the roof. And then the 250 is over here, the resultant of the distributed load on the leeward wall. So 60, 250, what is this? 436,085 divided by 662. That's the E sub x going to the left. So I've got a minus here. Okay, add all this up and you do get 0. So the equilibrium of the entire frame is valid in the x direction. What about the y direction? Take a moment now. You see the whole thing? What's in the y direction? Okay, sum of the forces in the y direction. Do I have to show you where these are coming from? Okay. What is this? That's A sub y. Remember that it's down. What's the 175? That is the vertical component of the suction on the roof. and then the 140,210 over 331, that's E sub y. Crank this out, and you do get 0. So I say, aha. I wanted equilibrium in the y direction. And then one more thing I promised. Okay, one more thing I promised, the sum of the moments about point E. And I'll see if that turns out to be 0 as well. The sum of the moments about point E is equal to 0. Negative 250 times 12.5, what is that? This is the 250. The moment arm is 12. That's half of 25. Remember, it's moment about point E. 60 times 31. That's minus 60 times 31. The 60 is referring to this right here. Acting along there. That's 60 pounds. Where am I getting the moment arm of 31? Okay, 25 here, plus another 6. 6 is half of 12. Then what? 175 times 17.5. That'd be this one. 175. What is half of 35? That's the moment arm. That is the 17.5. Minus 840 times 16. What 840? Here's the 840 right here. 840. Where am I getting that 16 from? Can you figure it out? The moment arm 16. How did I get that? Okay, how am I getting that? Okay, so this is 42. 42. This is 21. This is 21. Okay, so if this is 21, that means this must be 9. This is 25. 25 minus 9 is 16. Okay, maybe that wasn't the best explanation. Take it apart and you'll figure it out. 840 times 16 minus, what is this right here? That's the a sub x times 5. A sub x right here, moment arm 5. 5. Plus a sub y times 40. A sub y, 40. Okay, put this in a calculator. And what do you get? You do get 0. Okay, so I've verified the equilibrium of the entire frame. So a very long problem, but pretty easy if you take it a little piece at a time.